Good morning. We are now entering into the most fundamental and rigorous description of NMR. Previously we had used the vector notations for the magnetizations, magnetic moments, the fields, their interactions and so on. Although it is extremely useful, it becomes difficult to deal with those descriptions when we have to handle complex experiments involving multiple pulses and the response is difficult to describe. There will be many situations of equilibrium and non-equilibrium states. Various kinds of equilibria and non-equilibria can be present. There can be non-equilibria in the populations of the individual energy levels. There can be non-equilibria of the phase coherences between the spins. The phase coherence, as you know, results in transverse magnetizations, and the transverse magnetization evolve with a different time constants than the longitudinal magnetizations, and all of this has to be described in a more inclusive manner and an exhaustive manner and also more rigorous manner, which obviously cannot be done by the vector descriptions. So the recourse is to go into the more basic description of the spin systems using quantum mechanics. So a certain amount of quantum mechanical knowledge is required here, and I believe that the graduate students who are going to qualify in chemistry and some aspects of structural biology or things like that, or even physics, and they would have gone through such courses in quantum mechanics. And the description what we are talking about here is known as the density matrix description of NMR. Density matrix is not just a concept which is for NMR, but it is a very general concept, and therefore it deals with the description of any system in a very generalized manner. Let us begin by looking at the wave function of a spin system. In quantum mechanics you describe a system by a wave function, which is of course a vector, and if you want to represent it as a vector, you represent it as a vector with an amplitude and a phase, and almost invariably the wave functions are described in quantum mechanics as in some kind of a superposition of various eigenstates of a particular system. For example, here the wave function psi of t is described with the superposition of various individual eigenstates of the spin system. Here these are the individual eigenstates, and for the spin states, if you have a nucleus with a spin I and its azimuthal quantum number is m, and we have already seen that it has 2I plus 1 eigenstates. Okay. So let us look at that in somewhat more detail. So if I have a nucleus with a spin value of I, then I know that m takes 2I plus 1 values. For example, if I is equal to half, then we say it has the alpha state and the beta state represented like this, right. There are 2 states, 2I plus 1 is equal to 2. If I is equal to 3 by 2, then I have 2I plus 1 states are 4, then I will have different 4 number of states. If I have 2 spins, for example, this is for one spin, this is for a single spin. If I have 2 spins, then each one of them can have alpha and the beta state. So this can have the alpha beta states, and this other spin can also have the alpha beta states, and therefore I will have a total of 4 states, total 4 states, which we represent as alpha alpha, alpha beta, beta alpha and beta beta. This we have seen before when you were actually discussing analysis of spectra as discussed by Professor Ashutosh Kumar. Suppose I had 3 spins, all of these are spin half systems. if I have 3 spins, then how many states I will have? I will have alpha beta for 1, alpha beta for the second, alpha beta for the third. So, I will total of 8 states. Okay. So, therefore, we write it as alpha alpha, alpha beta, beta alpha, beta beta, and then here I multiply this by alpha here, alpha here, alpha here and alpha here. Then in the same manner alpha I have beta here, then I have here alpha beta beta, beta alpha beta and beta beta beta. So, a total of 8 states. So, like that we will have different wave functions. We represent the generalized wave function as a superposition of these individual eigenstates. These eigenstates are not time dependent, these are stationary states, but the wave function itself evolves with the time. Therefore, what we do, we represent this as a superposition of the states where the coefficients, these coefficients are time dependent. CMT, this is the coefficient which is time dependent. The wave function psi of t is time dependent and these UM's are stationary states, and therefore to get this time dependence here you write these coefficients as time dependent numbers. Okay. And since the wave function is a complex wave function, because it is complex in nature, as I said, it is a vector, it has an amplitude and it has a phase, the coefficients themselves CMTs, these are also complex in nature. So, these are complex. Complex numbers, and the various eigenstate, the states UMIs, these constitute an orthonormal set. Orthonormal set, what does that mean? So, you have here for example for the alpha alpha state I have alpha alpha, this is equal to 1, and but alpha beta is equal to 0. Okay. So, for the 1 spins case, when you have the 2 states here, alpha alpha is 1, alpha beta is 0. Likewise, if you have the beta alpha, it is 0, and beta beta is 1. Similar thing applies to all other states in your spin system. For the 2 spin state, you will have 4 states and all of them are orthogonal to each other, and they are also normalized because individual matrix elements of these are equal to 1. Now, so this is the generalized description of your spin system. We represent it as a wave function as a superposition of various eigenstates of the spin system. Now, when you actually make a measurement of an observable which is represented by an operator, for example, you may be measuring the X magnetization or the Y magnetization or something like that, then we observe the time average of an ensemble, right. So, here we have, this is for individual spins. Individual spins are represented that way. Each spin evolves in a particular manner. For example, in the classical way we noted that each spin is precessing around in the cone, surface of a cone. Each spin precesses, right. When it precesses, it acquires a phase, phase keeps changing. That is what we say, its time constant is, I mean the CM, the coefficient is changing, the phase is changing. When we say the complex numbers, they have also an amplitude and a phase, therefore their phase is changing. So, each spin has a particular value of Cm of t. Now, when you are making a measurement on an ensemble which consists of trillions and trillions of spins, so what we will measure is a ensemble average or the time average, same thing as called the time average of a particular spin over a long period of time. Okay. So, this is described by what is called as the expectation value of the operator. Every physical observable is described by an operator, and you measure when you make a measurement, we say we are getting the expectation value of this operator. This is basically representing a time average, the ensemble average. So, how is that calculated? That is represented in this following manner. This is the standard notation for describing the expectation values. This is the standard notation. Here we have a ket here and a bra here. generally we represent in this manner, and if A is your observable on which you want to make a measurement, you write this expectation value in this manner. This is the psi wave function here and the psi wave function here. This is the complex conjugate on this side and A is here. The same thing is represented in different notation if you want to use the integral, because you want to take an average here, the summation. We take the integral psi star A psi. We notice here we are assumed that the psi stars they are normalized. That means psi star, this integral is equal to 1, otherwise you divide it by this integral here. So these are already normalized functions, and therefore you can simply write it as psi star A psi d tau. Now d tau is a volume element, which means it goes over all the variables in your spin system. Okay. For example, if you want to calculate the expectation value of mx, the operator for x component of the magnetization in terms of the functions umi, and then you write it in this manner, umx phi is equal to summation. Now you see here you have one summation for this psi, another summation for this psi, and therefore I will therefore have two indices here, one index for one wave function, the other index for the other wave function. Therefore I will have summation cmt star Cn, because this is, as I said, it is a complex conjugate here. Therefore here we will have a complex conjugate, and this will be corresponding from here, this side Cnt, and this is your umi corresponding to this and uni corresponding to this, and in between we have this mx operator. Okay, because since these are numbers, we can take this out and keep only these eigenstates and the operators here as in the vector notation in this matrix element representation, right. So these are numbers, the numbers can be taken out, these are numbers which can be taken out, and then we write this umi stays here, mx stays here, and uni stays here, and we have double summation coming going over the indices m and n. Okay. Now we simplify this notation slightly. Instead of writing this umi and uni, we simply drop the u and we will simply say m and n. Okay. So it is just to indicate that m is actually the eigenstate for a particular this one, and this is the n here. This corresponds to this and this corresponds to this. So this is just a simplification of the notation. Now what we do now is we define an operator which is defined in this manner. Okay. This we define this p of t, this is an operator. Now it is a time dependent. Remember, this is a time dependent part, right, this is time dependent. Therefore the operator which we want to define is also time dependent, and that is defined in this manner. N p of t m is given by cm star cnt. This term which is present here, we want to put it as a matrix of this form. The n and m keep varying, right, because therefore this will generate a matrix, each one of them this generate, as you keep varying n from all the states and m also for all the states, you will generate that many matrix elements. How many matrix elements will generate for this? So if n is equal to 4, m is equal to the n runs from 1 to 4, m also runs from 1 to 4, you will generate a 4 by 4 matrix. So like here, so this will be, you will generate a 4 by 4 matrix when you vary all the m's and the n's. Okay. So therefore now the expectation value psi mx phi is now equal to the same thing, this psi has come in between, this is not equal, this is basically what we have here, right. So we have put this n, so star t cm stays tr tn, this one is put here, okay, this is represented by this, and this remains the same as that. Okay, this is not required here. So therefore, and now this goes over this terms m and n. Okay. Now basis function, now this is again a basic rule in quantum mechanics, that when you have a complete orthonormal set, this summation of this type over all the states m, this summation is equal to 1. This is the ket here and this is the bra here. You take a sum over all these states, then this is equal to 1. Okay, this is the identity, and we can simply use this identity for simplifying this equation. You notice here this identity appears here in the middle, right. So from here to here this identity appears, right. Therefore if I take this sum summation m and take this portion of this equation, then this actually goes to 1. Therefore, this simplifies my equation. Okay. Now one more correction here. Once I remove this 1 of the summation, I do not need this. So, I will have only one summation and that is going over n. Okay. So, I will have n pt mx n, and now therefore, there is only one summation. Now what does this tell me? This tells me that I have, if I have a matrix of pt mx, this is one operator, this is another operator, the product of them is also an operator, and I can have a matrix representation of this operator if I want to write it like that. So this is the matrix representation of pt mx, and all these n, these are the diagonal elements of this matrix. Then I am taking a summation over all these matrix elements n is equal to 1, 2, 3, 4, 5, so like that. So depending upon whatever number of states are there, so you will have the summation over all those states. So that is called as the trace. So this is the trace of this matrix P of t mx. So this is the sum of the diagonal elements of the matrix P mx. Now in an ensemble, the different individuals will have different coefficients. As I said before, the different spins will have different coefficients, and therefore we will have to take an ensemble average in order to represent the expectation value correctly. So therefore, when you take the ensemble average of this operation, then we will have this same equation coming back CMT, and this is summation over the two indices m and n. The average will be taken over this, because this is not time dependent. If mx is not time dependent, this is not time dependent, because m and n states are not evolving in time. What evolves in time are the coefficients, and mx is my operator. Okay. M and m states are not dependent on time. Therefore, when I take the ensemble average, I take the ensemble average over these time dependent quantities, which are the C's. Okay. So now this I represent by a new operator to represent the ensemble average. I call that as rho of t. This operator, now instead of the P of t, when I take the ensemble average, without the ensemble average, this bar I had called it as P of t. Now with the bar I simply call it as rho of t, and this is called as the density operator. Okay. And density operator has a matrix representation depending upon the various states what we have. For instance, if I have a single spin, I will have two states, and therefore I will have a 2 by 2 matrix, and the two states are alpha beta here and alpha beta here, because in each of these sides, because n goes from alpha to beta, m also goes from alpha to beta, therefore I will have 2 by 2 matrix, which is, so there are 4 elements. So if I have a 2 spin system, I will have 4 states. So 4 states, how will I write that here? So I will have 4 states, alpha alpha, alpha beta, beta alpha and beta beta, and similarly alpha alpha, alpha beta, beta alpha, beta beta. So this will be 4 by 4 matrix, that is 16 elements. Therefore the density matrix, this is called as the density matrix. And so the operator which it represents is the density operator. So similarly, if I have 3 spins, then we will have 8 by 8 matrix and so on. So when you go to larger and larger spin systems, of course the density matrix also becomes larger and larger. Okay. So now what we have to do is, we have to understand the density matrix more clearly. So let us try and calculate the elements of this density matrix. We put this definition once more. A particular element of the density matrix is represented in this manner, right. Rho mn is Cn t Cm star t. Okay, this is one particular element of the density matrix. Now the coefficients Cn's, as I said, are complex quantity, and hence ensemble average can also be written as follows. Now what I do is, I simply represent this as complex quantities. So it has an amplitude and a phase. So for the C and T, I write it as some modulus of Cm and e to the alpha alpha m, and for CMC this is a complex conjugate here, therefore it has a minus. If it is minus I, this one complex conjugate will be the plus I. So therefore Cn Cm star T is the modulus of Cm and Cn e to the minus alpha n minus alpha m. Now this is the phase and this is the total amplitude, okay, where the alphas represent the phases and the Cm represent the amplitudes. This particular matrix element therefore has an amplitude and a phase, okay. Now let us see what is the consequence of this as we look at the individual elements. Here is we have to understand this very clearly. Every sentence is quite important. We can go slow and to try and understand this very clearly. At thermal equilibrium, say by the hypothesis of random phases, all phases alpha in the range 0 to 360 are equally probable, and hence ensemble average vanishes for m not equal to n. When you take an average over this alpha minus alpha n, all possible orientations in the space are possible, because every phase is possible. When I say phase, it is an angle in the transverse plane, right. So therefore all possible orientations are possible, that means all the off diagonal elements vanish. Whenever m is not equal to n, when you take an ensemble average, all the elements will vanish. M is not equal to n, we call it as an off diagonal element. When m is equal to n, we call it as a diagonal element. Now, so all off diagonal elements vanish, okay. Non-vanishing of off diagonal elements means there is a kind of a phase coherence between the individual spins in the ensemble. That is why there is no cancellation, complete cancellation does not happen. So some amount of phase coherence is present among the spins, and that leads to non-vanishing of the off diagonal elements. What do the diagonal elements represent? The diagonal elements, when alpha m is equal to alpha n, that means m is equal to n, then the numerator part actually goes to 0, right. Here m is equal to n, this one goes to 0, then I have a modulus of Cn square or Cm square. Now what does this modulus of Cn square represent? It represents the probability, right. When you took the summation, when you wrote the wave function as summation Cmt umi, then the coefficient actually represents, the square of that coefficient represents the probability that the particular spin is in that eigenstate, and therefore we are taking the superposition of the individual eigenstates to represent the wave function. Therefore the modulus of Cn square essentially represents the probability that the spin system is in that eigenstate. So therefore we write that in this manner, what is the probability? Probability tells me the population of the individual state, right. We have discussed this before. What is the probability that the spin is in the particular eigenstate, and that is essentially asking what is the population, and the population is given by the Boltzmann distribution. This also we have considered before, right. So therefore the rho mn represents the delta. When it is the diagonal element, it is e to the minus en by kt divided by z, right. If it is off diagonal element, then it is 0. So that is why we put this as delta mn. Delta mn is the canonical delta. So if m is not equal to n, delta mn means is the canonical delta is equal to 0 for m not equal to n, and it is equal to 1 for m is equal to n, okay. So therefore if m is equal to n, this is the diagonal element, and the diagonal element is simply e to the minus en by kt divided by z, and where z is the partition function. This is what we have seen. This is the result of the Boltzmann statistics. What happens next? Boltzmann statistics is given by this, the partition function definition we had given earlier here, and this is the summation over all the energy values, all the probabilities for the individual states, where n is the total number of states, right. So n, what we have here is the total number of states in this, on your spin system, that depends upon the value of I. For any I, you have the number of states is 2i plus 1, okay. So let me write that here, n is equal to 2i plus 1. N is equal to 2i plus 1 for particular, if there is a single spin, or if it is multiple spins, then it is the product of the two spins. If I have things like A and X, then I will have 2i plus 1 of A multiplied by 2i plus 1 of X. Okay. Therefore, for two spin half systems, I will have 2 here and 2 here, I get 4 by 4 matrix. Okay. So, that n depends upon the number of spins and the I values. So, this one's e to the minus En by kT runs over all the individual states. Now, we expand this as we did before as 1 to n 1 minus En by kT plus 1 by 2 factorial En by kT square and so on and so forth as an exponential expansion. Under high temperature approximation, we have seen that En by kT is much smaller than 1, and then Z can be approximated ignoring the higher order terms in this equation. So, when we do that, we see all the higher order terms are gone. I keep only the first one here, Z is equal to 1 minus En by kT. Okay. This automatically leads to a further simplification. Now, I separate these two. I write summation 1 minus 1 by kT summation En. Okay. This is simplification. Now, what is the summation En? In order to understand this, let us look at the energy level diagram once more here. Let us take I is equal to 3 by 2 for a single spin. The same thing applies to other spins as well. So, in the absence of any magnetic field, you have the degenerate states, all the 4 states are degenerate here. I is equal to 3 by 2 means is 2i plus 1 is 4. So, and these states now split when you apply the magnetic field, and they 2 of them go up and 2 of them come down by similar amounts. To the extent this goes up, this comes down, this goes up, this comes down to the same amounts. Therefore, you have a negative energy here and a positive energy there, and the total of this is 0. Okay. So, similarly, if you take 5 by 2, I will have 6 states here, 3 states up here and 3 states down here, and the sum of all of this is 0. Then, so in general, therefore, the summation En over all the states is actually 0. Therefore, this portion becomes 0. So, what happens? Therefore, Z is simply equal to the number of states. Okay. Now, here is a little bit of a digression to be able to follow the mathematics little bit better afterwards. Suppose we have the Hamiltonian represented as H, and if it has eigenvalues lambda I, and we often write this as Hi is the eigenstate, gives you eigenvalue lambda I and the state I. So, this is the usual eigenvalue equation, and if this is the case, then it follows that e to the power h, this is an operator, exponential operator of the same Hamiltonian, and this, if this is operating on the same state I, it gives me e to the lambda I. So, here lambda I is the eigenvalue, and here e to the power h is the operator if I take, then I will have e to the lambda I. Therefore, if I take this matrix element between the two states j and I of the exponential operator e to the h, then I will have j e to the lambda I, and that is equal to, now this is a number, e to the lambda I is a number, therefore I can take this out and put this as delta ij. That means if I is equal to j, then this is equal to 1, or if it is not equal to I is not equal to j, then this is 0, this is the Kronecker delta. Therefore, I write it as e to the lambda I take it as this out since this is a number, and then I represent this ji as delta ij, okay, Kronecker delta multiplied by e to the lambda I, and we are going to use that here. So, therefore, we wrote rho mn is now written as delta mn e to the minus En by kT by Z, right. So, and now I recall again that rho mn is 0 if m is not equal to n, then delta mn goes to 0, and if m is equal to n, then I have simply e to the minus En by kT divided by Z. This is the partition function, this is the partition function, and this is the probability, and this represents the populations. So, together I write this as rho mn is equal to delta mn e to the minus En by kT divided by Z. Now, let us write this in the matrix form like this. Rho mn is equal to, now we have seen that Z is equal to the number of states, so it is 1 by n, and then you have this ket here m and e to the minus En by kT n. So, therefore, essentially this, if I were to take this out, this I have m and n here, and that is delta mn. So, delta mn multiplied by e to the minus En by kT. Okay. So, this is the same thing written in this manner. Now, what I do for the En, now I know that the En is the eigenvalue of the operator H, or when Hamiltonian operates on the state n, it gives me the eigenvalue En. Therefore, here I will put this as the result of the exponential operator operating on the state n. So, instead of En by kT of multiplying on the state n, I write this as now the coming out as the result of the operation of the exponential operator operating on n. So, therefore, now we have an operator term introduced here. Okay. So, the rho mn is now a matrix element here between the states m and n with the operator in the middle as e to the minus h by kt. So, therefore, if I write this also as in the operator form, so this also I write it as m rho n, and this is equal, then what happens? I can take this m n out. Ignoring this m and n, I will have rho is equal to 1 by n e to the minus h by kt. So, simply I take these out, these states out, and rho is equated to 1 by n e to the minus h by kt. So, this gives me a different representation of the density operator. This is the density matrix and this is the density operator. So, once again I will do the same trick, expand this density operator as a power series. Rho is equal to 1 by n is 1 by 1 minus h by kt plus 1 by 2 factorial h by kt whole square, and so on and so forth. Once again, under high temperature approximation, the higher order terms can be neglected, and I will have simply 1 by n 1 minus h by kt. So, h is, now we know what is the Hamiltonian h for a single spin. I can simply write it as minus gamma h cross h naught I z. This is the Zeeman interaction between the single spin with the field h naught, and that gives you minus gamma h cross h naught I z. Remember, this is mu dot h naught, and the mu dot h naught gives me mu z h naught, right, and mu z h naught is minus gamma h cross h naught. So, this is the, if you simply recall the previous lectures in the previous classes, what is the Hamiltonian, and you will simply see that, okay, this is for a single spin minus gamma h cross h naught I z. For spin half, so this will be number of states is 2, therefore, rho is equal to 1 by 2 1 plus gamma h naught h cross h naught I z divided by kt. Now, if you calculate the matrix elements of this operator, the matrix elements of rho will be rho alpha alpha, you can calculate this explicitly here, rho alpha alpha is equal to 1 by 2, this is the result what we will get. But I will show you the explicit calculations, and when you do this, the first element of the density operator matrix is equal to half of this much, and this is the fourth element for the 2 spin system, no, this is a single spin. For the single spin this is a 2 by 2 matrix, right, and there are 4 elements. Alpha alpha is 1 element, beta beta is 1 element, alpha beta is 1 element, and beta alpha is 1 element, and it turns out that when you actually calculate putting this Iz operator here, they calculate the matrix elements alpha alpha, then this alpha beta and beta alpha go to 0, and alpha alpha gives you half 1 plus gamma h cross h naught by 2 kt, and beta beta gives you half 1 minus gamma h cross h naught by 2 kt, and now if I put this all together, I will have rho is equal to half these 2 matrices 1 0 0 1 plus gamma h cross h naught by 4 kt 1 0 0 minus 1, right. So, this one is 1 plus, if you put it together, of course, this is the same thing is put in this manner. This one is here, this one is here, and these ones have entered into this term where these ones, and these zeros are coming, because alpha beta and beta alpha are 0, because you see, remember, this is alpha and this is beta here, and alpha here and beta here. So, this alpha beta, the cross terms are 0, and it is only the diagonal terms which are non-zero. Okay. So, I think this is a good point to stop, and we will continue with the discussion of the elements of the density operator in further detail in the next classes.